In this video, we're going to start to look at thermodynamics. Some key concepts for this section of the book is that energy is conserved. It cannot be created or destroyed, but it can take different forms. When we talk about biochemistry, whenever you hear me say the word enthalpy, it means heat. While whenever I say the word entropy, it means disorder. When we're talking about thermodynamics, we're going to talk about free energy, which is called delta G. Free energy is dictated by a change in enthalpy and a change in entropy. Spontaneous processes, those that happen on their own, happens if there's a decrease in this free energy. We can also calculate free energy in terms of reactants and products. In biochemistry, we have what's called a standard state, which is just a state everybody agrees on. That is 25 degrees C, 1 atmosphere, and a pH of 7. Organisms are never at equilibrium. We're open systems, and we constantly exchange matter and energy with our surroundings. And enzymes increase the rate of thermodynamically favored reactions. All right, so just some basic principles. Like I said in the previous slide, life is never at equilibrium. If you are at equilibrium, you are dead. Life is constantly taking energy and matter from our surroundings so that we can stay away from equilibrium. And this brings us to the first law of thermodynamics. Energy cannot be created or destroyed. We can only change the form it's in. For example, light is energy and heat is energy. If I hold something above the ground and let it go, I am converting different types of energy. When we talk about thermodynamics, we have these different ideas. A system is everything. All reactants, not reactions, all reactants, products, not productions, solvent, everything. You can have different types of systems, though. You can have an isolated system which doesn't exchange matter or energy with its surroundings. And by the way, surroundings is everything that isn't the system. You can have a closed system, which exchanges energy, and an open system, which exchanges both energy and matter. So isolated, think of a perfect thermos. Doesn't exchange anything. A closed system could be like a glass, like a glass ball. You can exchange heat by heating it up, but nothing can go inside or outside the glass ball. Open systems are like us. We can do both. So we covered the first law. The second law of thermodynamics simply states that the universe is constantly becoming more random, more disordered. Randomness and disorder actually mean the same thing. And life is constantly trying to fight against this. All life is trying to be more ordered. And we talk about randomness as entropy. And I want you to think of entropy as disorder. And it's called delta S. And we can define entropy a few different ways. One way is S equals KB ln W. So entropy equals a constant, KB is Boltzmann constant, multiplied by the natural log of W, which is the number of ways to arrange energy. And if we look at this example in the top right, we can understand what W means. So we have two chambers here, and right now the chambers are closed. We have gas on one side of the chamber. And if I open up this chamber, we all know what's going to happen. This gas is going to naturally or spontaneously go to the other side of the chamber. Because the gas molecules have more ways to arrange themselves in two sides of the chambers, or more space to arrange themselves than in one side of the chamber. So in picture A, W, or in this equation, W is lower in A than it is in B. So that's entropy, disorder. The universe loves disorder. The more disorder, the better. Enthalpy is heat. And really, when it comes to chemistry, we generally think of enthalpy as the types and kinds of bonds you have. And free energy, which we use to determine if something is spontaneous or not, we call that G. It's another way to say the ability to do work. And we have delta G equals delta H minus T delta S, where T is temperature in Kelvin. So this is a very important equation in all fields of chemistry, especially biochemistry. We talk about delta G's a lot. Maybe not so much in Biochem 1, but Biochem 2, we talk nothing but delta G. All right. So let's look at this equation. Delta G equals delta H minus T delta S. So if delta H is negative, you are exothermic. Heat is exiting your body, exothermic. While delta H is positive, your heat has increased. You are taking heat in endothermic. If delta S is positive, you have increased chaos, or you have become more disordered. While if delta S is negative, your chaos has decreased, or you have become more ordered. And delta G tells us if a reaction is spontaneous or not. So if delta G is positive, we call this as endergonic, non-spontaneous. Delta G negative, exergonic, spontaneous. We have lowered our free energy, so that process is going to happen spontaneously. While delta G of 0 means equilibrium. It's neither spontaneous or non-spontaneous. And when we talk about delta G, keep in mind this tells us nothing about the speed or kinetics of the reaction. Thermodynamics and kinetics are completely separate. If you have a reaction that is negative 1 kilojoules per mole, delta G, and another reaction which is negative a million kilojoules per mole, you cannot tell me which one is faster. And H, S, and G are what we call state functions, which means they only depend on the initial and final value, which makes it really great for chemists. We don't care how we got from initial to final. All we care about are initial and final, and this will make calculations much easier. Calculations you'll see in class. And that's it for part 1 of thermodynamics. We will continue part 2 in the next video. See you then.